Hello, everybody. This is Professor Jeff Wilkerson with an introduction to Poisson Statistics for the students in Classical Physics 2, Physics 182 here at Luther College. We have, as you know, if you've been part of the class, we've been using this photo multiplier tube as an example for a lot of different things, how you accelerate charges, given a potential difference from one stage to the next, how you create that potential difference by creating by using a resistive divider down here, and how you put capacitors over the late stages here to keep the voltage from sagging, because you need big bursts of charge when you get currents that are pretty high. Remember, we showed you different versions that we had made where you got those nice orange capacitors over the back end, and you see the voltage divider network right there. So this is a great device. We're going to use it today as an exemplar of Poisson statistics, and to say that if you have a photon that comes in and hits the photocathode is that gold surface that you see that's coated on the back of that front glass. This is a transparent photocathode. There are solid photocathodes for these things, but this is a semi-transparent one where the light comes in. It either hits the photocathode and converts, hits the photocathode and doesn't convert to a photoelectron, does convert to a photoelectron, or moves right on through and doesn't get absorbed in the photocathode at all. And so for a device like this, it would not be uncommon to have about a 20% quantum efficiency, we would say. About 1 in 5 photons that strike the surface result in a photoelectron coming out the back. But that's a purely probabilistic event. To say that you might have 3 in a row that make photoelectrons and then go on a long dry spell where many do not make photoelectrons. So any one, you can't say whether it's going to make a photoelectron or not. Any one photon that strikes the surface, it's got a 1 in 5 chance. That's all you can say. Okay, so let's think about an experiment. Let's say, suppose you had 20 photons striking the surface of that photocathode. With those 20 photons, you would expect, on average, 4 of them, if the quantum efficiency is 20%, you would expect 4 of them to convert into photoelectrons, and you would count 4 photoelectrons on average in your detector. Now, given that that's probabilistic, and any one might or might not convert into a photoelectron, sometimes you're going to make 3, and sometimes you're going to make 5. Sometimes you might make 7, and sometimes you might make 0. So you don't know what you're going to get. You're going to get a distribution. If you do an experiment where you shine 20 photons, count the number of photoelectrons. Shine 20 photons, count the number of photoelectrons. Shine 20 photons, count the number of photoelectrons. Shine 20 photons. You got it. If you just keep going like that, then you will count a different number of photoelectrons each time and start building that up. The number of photoelectrons that you measure there is described by the Poisson distribution up here, to say that, you know, the second photon doesn't care what the first photon did. Third photon doesn't care what the first 2 photons did. Fourth photon doesn't care. They're completely independent of one another. And what you get out on the other side are integer results. You can have 1 or 2 or 3 or 4 like this. This is governed by this Poisson distribution, this Poisson counting statistics. And it's given by this relationship. Mu is the mean number. In the example we just did, mu would be 4. And x is the number that you would expect to get. It's a probability of getting 0 or 1 or 2 or 3 or 4 or 5 or whatever you're interested in, given the mean of 4 in that example that we just did. So you would say e to the minus mu to the x, divided by x factorial. Now, if mu is big enough and you would expect to get, you're far enough away from 0. So if you're not far away from 0, suppose you had a mu that was somewhere in the neighborhood of 1, your distribution is going to look like this. It's got this long tail on it. It's truncated on the left side, 0, 1, 2, 3, 4, 5. And so it's truncated on the left side, and it's got this long tail out here on the right side. Does not look Gaussian at all, like the Gaussians we have been using in class. But you know your central limit theorem. If you don't know your central limit theorem, then read your textbook and learn a little bit about your central limit theorem. As this mean moves out here, the tails even out, and you can treat this as a Gaussian. And so the Gaussian fits work. If you get a mean of 15 or 20 or something like that, you have no problem at all fitting this with a Gaussian and doing a good job. But down here lower, you can't do that because you see it just isn't at all that normal distribution. So you have to go to the Poisson relationship here to calculate how likely you are to get a given value given a mean. You can always go to this. It's just a harder calculation, right? If the mean's 100 and you want to know what the likelihood of getting 99 is, you got to put a 99 factorial in here, and you got 100 to the 99th power. You can do all of this. You can use Stirling's approximation. You go in. You can do great work calculating this, but it's just much easier to go over and use your central limit theorem and treat it as a Gaussian once you're up in that high mu regime. So in any event, we're looking at the Poisson statistics, and particularly what we're going to talk about here today is to help you think about lab homework number 8, excuse me, the second of the two upcoming lab homework. So lab homework number 8, we're going to think about, and we're going to try something. We're going to try an application, and really that's what this is. This is a practice application of the Poisson distribution. And what we asked you to do there was to fit a Gaussian or two Gaussians to a distribution of values. And so try a single Gaussian fit, try a double Gaussian fit. But what I'd like for you to do is to do something that may or may not work. It may not meet all these criteria we mentioned earlier. You may not be able to say, these are independent events that don't depend on each other, whatever. This is all stuff you got to think about, okay? And we're going to try to do this as a goodness of fit parameter to try to start to understand whether the double Gaussian or the single Gaussian is a better fit. There are more sophisticated ways to do this. What we are doing now is starting to practice learning how to think about uncertainty in fits and such. So this is really a brute force sort of way we're going through to try to figure this out. This is just for us to get a handle and to get a feel for it. You want to go through this. You want to get this kind of feel for what various routines, what various approaches to understanding uncertainty are doing. And this is not necessarily the best, but don't let anyone ever fool you. Don't let anyone ever tell you that there's one and only one way to understand uncertainty in an experiment. You just need to think it through and think about how your uncertainty is working for you. But what I'd like for you to do is for the practice, this is just for practice for what we're doing for lab homework number 8, is to take each bin each bin of your histogram has a certain number of counts in it. Okay, so each bin of your histogram here, suppose there's some number n counts in that bin of the histogram. Now, what you can do is you can say, what you can realize is you can say, if you do a single trial experiment that counts integers, and those integers are independent from each other, those measurements are independent from each other, those events are independent from each other, and you count them one time, you do a single counting experiment, and you count 50, well, that's your mean, right? But you only did one, your mean is 50. And so that's the mean that you have right there. What we know, we won't show this. There are plenty of statistics books out there that show this. I don't know if your book shows it or not. There are plenty of them out there that walk you through this. What we know is the standard deviation, the uncertainty in this case, is equal to the square root of the mean. But if you only did a single trial, the mean is the number that you counted in that single trial, right? So the mean in the case where you went and this bin had 4 in it, the mean is 4 because you only measured the number in that bin one time, right? You said, I measured the number that fell between x1 and x2, and the number that fell between x1 and x2 was 4. That's a single trial measurement. The uncertainty in that mean is the square root of that mean is 2. Okay, so this is the way we think about any counting experiment like that you do a single time. You do a single counting experiment. It meets our criteria for Poisson statistics. Again, our example might or might not, but we're using it as practice. And to say it meets our criterion for all the criteria for Poisson statistics, then we would say the standard deviation is 2. Sometimes we look at the fractional deviation, sigma over mu, is going to be the square root of n over n is going to be equal to 1 over root n. So your uncertainty as a fraction of your mean gets better with the number of counts, 1 over the square root of the number of counts. So if you take 100 times as many counts. So if you're doing a radioactive decay experiment, for example, and you take 100 times as many counts, you're going to have 10 times better fractional width of your distribution. Your distribution looks like that. Sigma over mu is going to be 10 times better with 100 times better counting statistics, 100 times more statistics. So in this case, let's get back to our example then. So I would like for you to look at this. If you say, if this bin has 4 counts in it, treat that as a Poisson experiment, counting experiment, where you counted 4 events in this bin and take the uncertainty in that to be 2. So you can put an error bar. You can put a 1 standard deviation error bar on there. And I'd like for you to go back to your histograms and do that. Put a 1 standard deviation error bar on there where sigma is equal to the square root of n for each bin down through there. So you do that for each bin. Then, for practice, what I'd like for you to do is I'd like for you to take each of your fits, double Gaussian fit, single Gaussian fit, and to measure at each bin. There's your fit value. There's the value that comes from the fit. There's the value that was in that bin. So take the center of the bin, see what the value of your Gaussian or double Gaussian fit was at the center of that bin, and measure that in terms of standard deviations away. So you look at your fit and you say your fit would be, your fit right here missed high by 1.4 standard deviations, for example, in that bin. Okay, and this one maybe missed high by 0.7 standard deviations or something along those lines. Then we can assess this a few different ways. We got different ways that we can go here. And this isn't, maybe I said this before, I don't know, this isn't by far the most sophisticated way to do a goodness of fit analysis, but it is a way, and it's a way for us to practice thinking about what goes into this. And we want to learn, think about some of the mechanics underneath these goodness of fit tests, and that's really what we're doing here. We would, in a first year physics class, very few people are doing this kind of work, but I think it's important for us, and where you are developed to the point where I think you can make this work and you can understand this and you can do this, and it's really going to be able to help you as you go forward. And so we're looking at this in a sort of very basic mechanical way that we can build on in the future. As we're near the end of the year here, as we get ready to transition to being second year physics students, this is great stuff for us to be doing, to be thinking about. So what I want to do is to sum up all of those deviations like that, and to say one possibility, one way I'd like for you to test your goodness of fit, is just to do a sum of these, to say point by point by point by point by point at each bin, measure how many deviations you were high or low, and then do the sum of the fit minus the fit minus the actual value in your bin right there divided by sigma. Okay, and we're going to sum over I bins, however many bins are there. So sigma sub I, value sub I, fit sub I. So go each bin, increment by 1. Bin 0, bin 2, 1, bin 2, bin 3, bin 4, bin 5, and sum that value up. And better do an absolute value, right? If you're low half the time and high half the time, that'll average out and say you're perfect, but you could be way off. You could be a 1,000 sigma low and 1,000 sigma high and come up with 0 if you don't do an absolute value. So let's do an absolute value right there and do that sum for me, and then compare that number for the double Gaussian fit to the single Gaussian fit. But there's another way to think about that. Suppose you have 15 bins across here, and you would expect from your Gaussian statistics, from your Gaussian probabilities, if your normal distribution, you would expect to get a 2 standard deviation, rounding off here. You would expect to get a 2 standard deviation fluctuation high or low about 5% of the time. Okay, so about 1 in 20. So let's say you had 20 bins across here. Your expectation is that one of those bins is going to be 2 standard deviations high or low. Okay, if you find 2 that are more than 2 standard deviations or 2 standard deviations or more away from the fit, that's twice as many as you would expect. But it's not, given the square root of n that we're thinking about right here, it's not that many, it's not that much more. If you get 3, then that's starting to get to be a bit more, but 3 is still not too many fluctuations right here. If you get 4, then you can start to think about how many times did you miss by 2 standard deviations or more, and how many times just from sheer randomness, would you have expected to miss by 2 standard deviations or more? So I want you to look at both of those things for the homework number 8. I actually forget if I wrote that into the second half of number 8 or not, but I'm telling you right now, I want you to look at this sum, and I want you to look at how many times you missed by 2 standard deviations or more. You can see how many times you missed by 2.5 standard deviations or more. You would expect those kinds of deviations to be pretty rare, right? You're getting to be 1 in 100 at that point. And 1 in 100, if you have 20 bins, you would expect that to only happen 1/5 of the time. So even 2 is starting to become very significant if you've got a 2.5 standard deviation. If you've got a 3 deviation fluctuation, then we can start to say, yeah, that fit's not very good. It's going to show up here too. But you can start to look at it and say, this is where it's missing, and this is where we need to tweak our fit, and this is what we need to do. So this is the kind of thing we're going to practice. Last idea I'm going to leave you with here. This is good. Think about the Poisson counting statistics, how we're using it to test goodness of fit as just an entree, just a way in to starting to understand goodness of fit. But the last idea here is completely different. And it's to say, one way you can use Poisson statistics is kind of fun. When mu is low, you can see how many times you would expect to get 0. Okay? 0 factorial is 1. Mu to the 0 is 1. And so the probability of 0 given any mu is equal to e to the minus mu. Now, if mu is too high, you have no chance of getting 0. Okay? But if mu is not too high, if mu is somewhere between 0 and 2 or 3 or 4, maybe 4, somewhere in that range, you will have some chance of getting zeros. 2 Luther students and I, a long time ago, shortly after I first arrived here at Luther, we did an experiment to measure infrared scintillation yield in xenon gas. And we used this fact to say we knew what the rate should be. We knew what the rate was. We put a radioactive source in there, and we counted events. And if you counted every event, we knew what count rate we got. And so then we could look to see, as we changed the conditions, if we got fewer and fewer counts, that meant we were getting zeros in this Poisson distribution. To say we were getting 0 yield from 0 photoelectrons. We were using a photomultiplier tube like this. You get 0 photoelectrons from your infrared scintillation light that you saw right there, and you can figure out what the mean number of photoelectrons was from the number of zeros, the fraction of zeros that you were getting. And we used that to deduce the infrared scintillation yield. So it was kind of a fun use of Poisson statistics. And this goes back 20 years. Again, a couple of Luther students that I worked with there have gone on to do great things. What I'm going to do, so you have a chance to look at it if you want to. I'm not telling you you need to look at it, but this was published in Nuclear Instruments and Methods, and we certainly have a subscription to that here on campus. So if you're on campus, you can see it. I don't know if others can. It's old enough now. Maybe everybody can see it. But anyway, I'm going to put a link to that paper where we use Poisson statistics to determine the infrared yield, scintillation yield of xenon gas at different pressures. So you can see an application of it, kind of fun application of Poisson statistics, and think about what we want to do. Watch this video a couple of times. Read homework number 8 and come with questions and talk to me. That's what we got for you. That's a very quick, dirty introduction to Poisson statistics. Let's talk about it more when we get in class. Take care, everybody.